All right, hello. My name is Tim Reeves. I'm an application engineer with MathWorks, and I'm here at IMS 2024. MathWorks is showing a number of exciting demos during this conference, and in particular we have an example here of where we're making use of MATLAB, a key-site field Fox analyzer to characterize an RF component, and this workflow will aid in the development of cavity filters during the prototyping process. Here you can see that we have the interface between the key-site field Fox analyzer and my laptop via the field Fox remote display. On the right-hand side here, we have the application here where we can go and create the interface so as to be able to do data analysis in MATLAB for this high-performance cavity filter. This particular workflow goes and increases the amount of automation in the prototyping aspect of the cavity filter design process. The basic setup here of this workflow is that the application can be used to get data, access data from the instrument, be able to do analysis and model extraction of the measured S parameters, and then generate model outputs for the tuning and mechanical development of this filter. So in this first pane, we can see that there are push buttons to access the network analyzer to read in the S parameter data and then write that S parameter file to a data. Also, if you have S parameter files that are available on your laptop or computing device, you can read those in. With a minimal number of inputs, you can go and be able to characterize the cavity filter here. So if you specify the filter order and then the approximate center frequency and filter bandwidth, one can go and then be able to extract a normalized low-pass admittance parameter representation of the filter. Now, one of the things in the development of coupled cavity resonant structures is there's what's called the coupling matrix, and the coupling matrix serves as kind of the golden reference or the one truth in cavity filter development workflow. This ties together the software development process and then the actual physical prototyping. So from the previous model that was extracted, a coupling matrix can be extracted, and there are multiple representations of the coupling matrix that can be provided here. So with just push buttons, different representations, the transversal coupling matrix and the folded coupling matrix can be generated. Via use of a Gram-Schmidt transformation process, other coupling matrix representations can be achieved. And then here on the right-hand side, we can see how an estimate of the unloaded Q factor, which ties back to the insertion loss of the filter, can be estimated. With any model extraction process, the validation and verification of the model is a key aspect. In this case, we make a comparison of the S parameters measured from the filter and then compare those against the generated S parameters from the model. We can see here that there's a favorable comparison between the measured results and the extracted results. To make this really useful in the cavity filter development workflow process, specifically either during the electromagnetic modeling portion or the physical prototyping, it's useful to go and take the extracted model and to be able to go and represent it in terms of a nodal representation. Once we have it in this nodal representation, we can go and add lumped element components so as to be able to tune the response to meet what would be the response of the golden reference model. So here we can see that from the previous step, we're able to go and generate the nodal representation, and then we're able to add lumped elements at each resonant section to be able to go and first of all tune the resonance frequencies of each of the respective filters, and then between adjacent resonators, we can go and add inductors so as to be able to tune the coupling in between the respective adjacent resonators. In combination with a gradient optimizer and going and selecting a couple of key cost functions, i.e. the value, the reflection coefficient value at each of the reflection zeros, along with setting up the standard deviation of the local maxima, an optimization or calculation of these lumped element values can be performed so as to achieve an equiripple response. The results from this optimization can be used to direct the tuning of each of the individual tuning elements within the filter, and so as to be able to achieve a result where the measured results compare directly to the optimized results. These susceptance values need to be driven to zero, and this is achieved by making mechanical adjustments of these tuning screws, going and extracting a model, and to subsequently achieve element values that lead to these susceptance values going to zero, and that will go and then allow for an extracted model that corresponds with the extracted golden reference model. So more information about this workflow can be obtained at MathWorks.com. Specifically, if you go to the RFPCB toolbox at the MathWorks product page, there's also a video available on this specific topic, extracting filter models, again at MathWorks.com. Thank you for your attention. Have everybody enjoy the show.